last week, right, we were talking about one particular problem in quantum mechanics, right, which is the particle in a one-dimensional box. And we figured out a bunch of things for that, right? We figured out what are the possible energies. We figured out what are the different pure states, what we could call the quantum states of the particle in a 1D box. And we figured out how if you start with any arbitrary initial condition, you can predict what the wave function is going to do in the future. And then once you have that, you can get out the probability density in the future, and you can get out the expectation values in the future. What I want to get started with today is going to be doing the analogous calculations for a different physical system. So that means for a different potential energy. And this will make a nice point of comparison, right? So you can see then what is similar and what's different between two different physical systems. Okay. So the thing that I want to get started with today is the harmonic oscillator. Okay, so let me begin by reminding you a little bit about the harmonic oscillator in classical mechanics, and then we'll see what's the analogous thing to do in quantum mechanics. Okay. So classically, you know, a harmonic oscillator is something like a mass on a spring. So here's a spring, here's a mass. Okay, and the mass moves by some distance x, and then there's a restoring force. Okay? And so the restoring force is negative kx. Okay? And so if we want to solve this problem in classical mechanics, well, you've seen this years ago, but I'll just remind you, okay? So the classical solution is to say, well, we want to solve that the mass times the acceleration is equal to the force, right? So the mass times the second derivative of position with respect to time is equal to minus kx. And then we divide through both sides by mass over there, okay? And we say, this is an equation where the second derivative of the position with respect to time is a negative constant times x, right? And so the solution has to be that x as a function of time is something times the sine of omega t plus something times the cosine of omega t, where here this omega has to be the square root of k over m. All right, so omega is fixed in this solution. A and B can be anything. And so these parameters are determined by the initial conditions. Okay, so this is one thing that you remember from classical mechanics about the harmonic oscillator. Another thing that I'm sure you remember is the potential energy. That the potential energy of the harmonic oscillator is the negative integral of the force. And so, whoops, I didn't mean F, I meant potential energy. V of X is positive 1/2 kx squared, right? And so the force is the negative derivative of the potential energy with respect to X, right? So negative kx. Okay, so this is, one of the standard problems that you learn about in university physics, right? Or wherever you begin studying classical mechanics. And one of the reasons why you learn about it is that it's a nice, simple problem which has an exact solution, right? And so it's sort of illustrative of how to solve stuff in classical mechanics. And another reason why you learn about it is that it's a good approximation for any oscillation. So, if you have any old potential energy function, some v of any coordinate x, right? And, it has some complicated shape, whatever, all right? But it happens all the time that you get small oscillations about a particular minimum. About this minimum, for example, right? Maybe you have some particle that can oscillate back and forth around that minimum. And if you want to know something about the frequency of oscillations, you could say, oh, let's approximate that minimum by a parabola. Something like that, okay? And so we'll say, approximate this thing by a parabola. And so we could say V of X is approximately 1/2 times the second derivative at this point, x0, times x minus x0 squared. So V of X is approximately V of X0 plus this quadratic thing. Okay, so this would be a power series to approximate V of X. And so then we could say, oh, well, this is something like a spring constant. And then, this problem maps onto the harmonic oscillator as long as the oscillations are pretty small so that the higher order terms in this expansion are negligible. Okay, so that's a practical use for the harmonic oscillator problem in classical mechanics. And the same works in quantum mechanics, right? People study the harmonic oscillator in quantum mechanics also for both of these motivations, right? So one motivation is it's a standard problem that is exactly solvable. And so we can work out the features of this problem. And then a second reason is that it's a good approximation for any kind of quantum mechanical oscillation. And so if we have any arbitrary potential like this thing, again, we could approximate it by a quantum harmonic oscillator and say something about what are the quantum oscillations about a point like that. Okay, so that's supposed to be the inspirational motivation for studying this thing. Okay, so let's talk about how to do it. Okay. So for the quantum harmonic oscillator, you know that when we've been working with Schrodinger's equation, we don't really talk about forces much, right? We talk about potential energy, right? Potential energy is what goes into Schrodinger's equation, okay? And so we are going to have a potential energy to start with, okay? So the quantum harmonic oscillator is a potential energy. V of x is 1/2 k x squared. And to begin with, there is a change of variables that everybody in quantum mechanics always makes. Okay, so for some reason in quantum mechanics, nobody ever talks about the spring constant k. Instead, what they do is use this equation that omega is the square root of k over m, and they take that and rewrite it as k equals m omega squared. All right, and so they then take our potential energy and say it is 1/2 m omega squared x squared. So this is the potential energy that we get started with, okay? And I guess the reason for doing it for writing this potential energy in terms of m and omega instead of k is just that this is going to make some of the other equations easier later on. Okay? You know, you should just accept that this potential energy, V of x is this thing, this is totally equivalent to the harmonic oscillator that you're accustomed to. It's just with writing a potential energy equation instead of a force equation, and writing the spring constant as m omega squared instead of k. Okay, but those are just two changes of notation. It's still the same physical problem. Okay, so that means now we want to solve Schrodinger's equation with this potential energy. Okay, so we have Schrodinger's equation, the same as before. Okay, so I h bar d psi dt is equal to minus h bar squared over 2m times the second derivative of psi with respect to x plus v of x psi of x and t, where this v of x is 1/2 m omega squared x squared. Okay, so this is the partial differential equation that we want to solve. The beginning of the solution is exactly like what we did before, okay, where we separate variables. Okay, and so we can say for separation of variables, we want to say that the potential, the wave function as a function of x and time, that's the uppercase psi, that is our lowercase psi of x times a function of time. We want to put that into Schrodinger's equation and solve for the function of time. And we've already done that, okay? We already know how that part of the solution works. And So we know that the function of time is the exponential of minus I energy t over h bar. Okay. So the time-dependent solution, the time-dependent solution is a time-independent solution times this exponential factor. And then the position part, that is this lowercase psi, has to satisfy the time independent Schrodinger equation, which is that the Hamiltonian acting on psi is equal to E psi. Right? And in this case, that means that minus h bar squared over 2m times the second derivative of lowercase psi with respect to x, plus 1/2 m omega squared, m omega squared x squared times psi of x is equal to E times psi of x. Okay, so everything on this slide, up till now is like what we're used to. That works for any potential energy. But now comes a new thing, right? That we want to solve this time-independent Schrodinger equation. Written out like that, okay? And we want to solve it not just in a box, right? There's no box in this problem. Right? The particle could go anywhere, right? The spring could be stretched anywhere in this direction or anywhere in that direction. Okay? So we want to solve it for x from minus infinity up to infinity. Okay, so that's our goal here. That's our our goal for the week is to solve this differential equation and use that to figure out stuff about the quantum mechanical harmonic oscillator. Okay, you clear so far? All right. Good. So, whoops, what am I doing here? Okay, so now what? Now how do we solve this thing? Okay, there's a question, how? How do we solve this thing? All right. Well, the textbook by Griffiths provides actually two methods. Okay. And the two methods are what he calls algebraic and analytic. So let's talk about what these two things mean. Okay, by the algebraic solution is what I would call clever tricks with operators. And there are some nice features of this, right? And one is that it's sort of conceptually interesting. And it it teaches you about operators, right? And so I've mentioned operators already in this semester, but it goes into learning more things about operators. Okay. And another nice feature of this solution is that it is not too much work. I mean, it's some work, but it's not horrible. By comparison, the analytic solution is more like a standard method for solving a differential equation. And from my point of view, I would say it's kind of tedious, actually, and it's lots of work. And so what I'm going to do, as you can guess from the things that I've written here, I'm going to do number one, right? I'm going to do the algebraic solution, and I'm going to skip over the analytic solution, okay? And so I will encourage you to read the analytic solution in the textbook for comparison, but I cannot bring myself to actually present it in class. Okay, so read that one, but I'm not going to do it. Okay, and I'm going to do the algebraic solution number one instead. Okay, now, as I said, I perceive this thing to be kind of a trick solution, right? And now, when I say something is a trick solution, you know, the essence of a trick solution is that I'm going to do stuff which seems as if it's not related to solving the problem, okay? And you're going to be thinking to yourselves, okay, it's true, I guess he can do that. Oh, why is he doing it, right? And maybe I'll spend an hour doing stuff and you'll be thinking, why is he doing any of this stuff? It has nothing to do with our problem. And then all of a sudden, poof, out comes a solution, right? And it's like pulling a rabbit out of a hat, okay? And so, you know, that's what I call a trick solution, okay? And so that's what I'm going to do now, okay? So I'm going to start showing you stuff, right? Which superficially seems as if it has nothing to do with the problem that we're talking about, okay? And you can believe me or not believe me about whether you think it really has to do with this problem. Okay. But the stuff that I'm going to show you with operators, you know, it's good stuff to know because it's going to come up elsewhere in the semester also, apart from the harmonic oscillator. Okay, so let's talk about operators. Okay, so the concept of an operator, right? It's a mathematical concept that comes up all the time in quantum mechanics. And, you know, it's a mathematical concept to describe something that changes one function into a different function, right? And so you start with a function f old, okay? And then there's some operator, A, let's call it A, that operates on that function, okay? And it produces a function, F new, okay? So it's, you know, it's like a machine, right? F old goes into the operator and it produces F new, okay? And the input comes in from the right and it goes out to the left. That's a kind of conventional mathematical notation, right? And so we write this as F new equals A operating on F old. So this is a function. This is an operator. And this is a new function. Okay. And so the hat symbol over the operator, this is a graphical reminder that something is an operator. Okay, here I'll say a hat means an operator. The same way that if you write an arrow over a letter, it means a vector. But as with vectors, you know that sometimes professors forget, okay? And so you just have to accept that sometimes we forget, okay? But that is life, you have to deal with it, okay? So, I told you, this is as if, the operator is a machine. That's maybe kind of an old-fashioned analogy, right? Maybe a more modern analogy would be in software, right? So if any of you are accustomed to writing software, you could write a subroutine, right? Which is sitting and waiting for its input. And then when the right kind of input comes along, right, it goes into the subroutine and produces the output. Right? And so one function is the input and another function is the output. Okay, so to think about maybe the simplest example in the world, we could say 2 hat is the multiply by 2 operator. Okay, so that means, if f old of x is x squared, then f new of x is 2 hat acting on f old x. And so it's 2x squared. That's kind of an easy example. Okay, so let's make a table with some other examples. So here is f old of x, and then over here will be f new of x. Okay, so I said with 2 hat, right? If f old of x is x squared, then f new of x is 2x squared. Okay. Another example that we've already dealt with is the position operator, x hat. Okay, so that means multiply by x. Right? So if f old of x is x squared, then f new of x is x cubed. Another kind of operator would be to take the derivative. I could write it as d by dx with a great big hat over it. Right? And so if f old of x is x squared, then f new of x is 2x. Or for another example, is the momentum operator. Okay, so that is minus I h bar d by dx. Okay, so if f old is x squared, okay, then I'm going to take the derivative and multiply it by negative I h bar. Okay, and so I get negative 2 I h bar x, like that. Okay, so here are several examples, right? And we can make more examples. We could have an integral operator, right? Or other kinds of things. I should emphasize that these examples are all linear operators. A linear operator is an operator that satisfies two criteria. Okay, so one rule is that a linear operator acting on a constant times f old is equal to that constant times the linear operator acting on f old, which C is a constant. Okay. And another property is that the operator acting on a sum, acting on f old plus g old is equal to A acting on f old plus A acting on g old. So a linear operator has to satisfy those two rules. Okay. You can check, right, that the four examples that I have up here are all linear operators, right? If you multiply by 2, if you multiply by x, fine, that's commutative. It works in both of those equations. If you take a derivative or a derivative times something, fine, no problem, okay? By comparison, not all operators are linear, okay? And so let me just give you a few examples of nonlinear operators. Okay, so let's see if I want to make my table here for operator f old f new. Okay, so I could have an operator that's called square the function. I don't have a good notation for that. I'll call it square the function hat. Okay, and so if f old is x squared, then f new is x to the fourth. Okay. And if f old is 2x squared, then f new is 4x to the fourth. Okay, so you can see it's not linear, right? Because it doesn't satisfy this thing. Okay, now maybe that one is obviously not linear. Let me show you another one that's maybe not so obvious. How about if I have an operator called add to hat? Okay, so if f old is x squared, then f new is x squared plus 2. Okay. And if f old is 2x squared, then f new is 2x squared plus 2. Okay. And you can see that 2x squared plus 2 is not double x squared plus 2. And so this is another example of something that is not a linear operator by this definition of the term linear. That one is sometimes not obvious to students. And the reason is that, you know, in your education, we give you different definitions of the word linear, right? Sometimes we tell you the word linear means you know, something that's linearly proportional to x, right? Like a function y equals mx, right? And sometimes we tell you, oh, if you have y equals mx plus b, that's linear, right? What I am telling you now is the definition that b has to be 0, right? That it can't be y equals mx plus something. It has to be just y equals mx. That's the definition of linear, okay? This may contradict what your high school algebra teacher taught you. Too bad, okay? You're in my course now. And so you have to use my definition of the word linear. I'm sorry, the world is inconsistent that way. Now, in quantum mechanics, we always work with linear operators. So for the rest of the semester, I only want to think about linear operators. Okay? That's why I don't even have a good notation for these things, because I don't think about them in the quantum mechanics course. Okay, and so I'm only going to work with linear operators like these examples. Okay. Now, let's talk about how to combine operators, okay, which is called composition of operators. Okay, so that means how can you have a situation where a function goes into one operator and then the output of that goes into another operator and you get a final result, okay? So that means you could say F nu is the operator B acting on the operator A acting on F old. Okay, so that means that F old goes into A, okay? A produces its output, okay? Then the output of A goes into B, and B produces its output. That's what makes our new function, right? We normally write this without parentheses, okay? So we write it as B acting on A acting on F old, like that. Right? And so when you see something written out like this, you have to read from right to left. Okay? And so F old goes into A, then the output of that goes into B, and then the output of that, that's your new function. Okay? Now, when we have this, we often will say this combination BA makes a combined operator C. So this whole thing is C acting on F old. Okay. This is now a way of making a composite operator which comes from the combination of A and B. And now we can get a little bit more abstract. And so in a level of abstraction, we could say, instead of just thinking about these things acting on a function, we can just say, let's combine the operators as abstract objects. And so we will write this as C is equal to BA. Right? So this is saying here we have combined two operators, A and B, to make a third operator, C. So it's as if you're writing software and you have two subroutines, and you always want to feed the output of one subroutine into the input of another subroutine, okay? And so you package the two subroutines together so that whatever input comes along goes through one, and then it goes through the other, and then it goes back out, okay? And so C is the combined operator that does the job of both of them. Now, when I write it this way, it looks as if it's multiplication, but it's not multiplication. It's the composition of operators. So let's think about some examples of that. Okay. So here, my table of examples. So here, F old and F new. Okay, so if the operator is 3 hat, 2 hat, right, and F old is X squared, then I take my X squared, I multiply it by 2, then I multiply it by 3. So my new function is 6X squared. Okay. Or if the operator is 3 hat, X hat, okay, and my input is X squared, then I'll multiply it by X, that makes X cubed. Then I'll multiply it by 3, that makes 3X cubed. Or for maybe a more interesting example, if I have X hat and d by dx hat, and it's acting on X squared, okay, if I first take d by dx, I get 2x. And then I multiply it by x. And so I get 2x squared. Now, this is all using a specific input function of x squared. Now, you might wonder, what would happen if I had a different input function, right? What if I had x cubed or x to the 4th or sine x or anything else, right? So in order to figure that out, it's good to use a general input function. Let's just call the input function f of x without saying what it is. Okay? And then we would say, well, 3 hat, 2 hat, acting on f of x. Well, that is 3 hat acting on 2 f of x. So that is 6 f of x. okay? So from this, we can conclude that no matter what the input function is, we have that 3 hat, 2 hat equals 6 hat. So for any input function, doesn't matter if it's x squared or x cubed or whatever, right? For any input function, 3 hat, 2 hat equals 6 hat. Okay, and so this now is a general statement about the operators, 3 hat, 2 hat, and 6 hat, okay? That has nothing to do with what input they're acting on, okay? Let's do it with other examples, okay? So 3 hat, x hat on f of x. So that's 3 hat acting on x f of x. So that is 3x f of x, okay? So that tells us that 3 hat x hat is equal to 3x hat. Okay, and likewise with the derivative example, right? That x hat d by dx hat acting on f of x, okay? So this is x hat acting on f prime of x, right? Or it's x f prime of x. So as a general operator statement, right, x hat d by dx hat is, well, whatever you want to call it, x d by dx hat, like that. Okay, so this then is a set of rules about how to combine operators to make new operators, okay? This is what mathematicians call an algebra. All right, so you learned some kind of algebra in high school, right? About how to combine variables like x and y, okay? But in general, an algebra is how to combine mathematical objects. And so, at various points, as students, you've learned about vector algebra, right? How to combine vectors with dot products, cross products, things like that, right? Or you learn matrix algebra, about how to combine matrices. So here, what I'm showing you could be called operator algebra. How to combine operators. So when Griffith talks about the algebraic method for how to solve the harmonic oscillator, remember, that's what we're doing, is solving the harmonic oscillator, right? When he talks about the algebraic method, this is what he means, right? It's a method based on operator algebra. Okay, so now that I've said this, I can show you an important point, okay? And I'll even call it important. Okay. Operator algebra does not have a commutative law. That is, AB equals BA. Okay? This is not necessarily true. Sometimes it's true, sometimes it's false. It might be true or it might be false, depending on which operators you're working with. Okay? So let's see an example of that. Okay, so a good example would be with x and d by dx as two operators. Okay, so let's combine them in different sequences and see what we get. Okay, so if you have x acting on d by dx, acting on f of x, what do we get? Okay, that means x acting on f prime of x. So it's x, f prime of x. Okay. By comparison, if we have d by dx acting on x, acting on f of x, this is d by dx of x f of x, right? With parentheses like this. The same way we could have parentheses like that. Okay. So this is a derivative of a product. Okay. If we want to get that, we have to use the product rule. Okay. You have to remember the product rule that you learned in first year calculus. Okay. The derivative of the product is the first times the derivative of the second plus the second times the derivative of the first, which is just one in this case. Okay, so now we look at this and say, these things are not the same. Okay, so this is an example that shows us that x d by dx is not equal to d by dx x. Okay. So these two operators do not have a commutative law. Okay. And the word for this, if you're saying it out loud, is that x hat and d by dx hat do not commute. Okay, so this is what people say when they're speaking out loud. These two operators do not commute means you don't get the same answer if you put one first and then the other, or the second first, second and then the first. Okay, so if you have two operators like this that do not commute, then you might want to know how different are they? How different are AB and BA? Okay. Are they almost the same, or are they very different? Okay. There is a mathematical concept for how different are these two combinations. Okay. The mathematical concept for that is called a commutator, which is written like this with square brackets, and then you write one operator comma, the other operator, and close square brackets. And this is defined as AB minus BA. So if operators do commute, that means the commutator is equal to 0, right? That there's no difference between those things. If operators don't commute, then the commutator is different from 0. So let's figure it out for the two operators d by dx and x. Okay, so we want to know what is this commutator, okay? The way to figure it out is to let the commutator act on a function, right? I should emphasize the commutator is an operator, right? Because when you combine A and B, you get an operator, right? This is AB is an operator. BA is an operator. The difference between them is an operator. So the commutator is an operator. Okay, so the commutator of d by dx and x is an operator. Okay, if you want to know what operator it is, you have to let it act on a function. So you let it act on, for example, f of x, where f of x is any general input function. Okay. What this gives us is d by dx on x on f of x minus x acting on d by dx acting on f of x. Okay. So we already figured out both of these things on the last page, okay? So d by dx acting on x, acting on f of x, is this combination, okay? So this is, okay, x f prime of x plus f of x. Okay, that's the first piece. Minus the second thing, x d by dx of f of x. It's this line. It's x times f prime of x. So x f prime of x, like that. Okay. Now, the x f prime of x cancels there and there. And so this is equal to just f of x. Therefore, okay, we conclude that this commutator acting on f of x just gives you f of x. Okay. Now we can make the abstraction and say if the commutator acting on any function f of x just gives you that function, that means that the commutator as the sort of abstract operator d by dx comma x as an operator is equal to 1/2, right? The operator that means multiply by 1. Now, I told you that I sometimes forget to write the hat over an operator. But if the operator is as simple as just multiply by a simple number, a constant number like 1, then I and everybody else leaves off the hat. Okay, and so we just say this is equal to 1. So you'll notice that the way I got to this step is by letting the commutator act on a test function, f of x, and seeing what happens to the test function. Okay? You really have to go through that step. Okay? A really common mistake that students make is to leave off that step of having something operate on a test function, because students often think that they can figure out a commutator just by doing it in their head. Okay, that's not a good idea. That's not for beginners. Okay, and so as a beginner, you really have to let something act on a test function and see what happens to the test function. And that way, you know when you have to use the product rule. And it happens all the time that you might have to use the product rule. Okay? Whereas if you were just trying to do it in your head, you would probably forget to use the product rule. Okay, and so I really recommend, this is not a place to skip steps. This is a place where you really want to let it act on the test function and see what happens. All right, so here now we get something with the commutator of these two operators, d by dx and x. Okay, now one thing we can do with that to apply it to quantum mechanics is to say, well, this d by dx operator, that's kind of related to momentum. Okay? So we know already that the momentum operator is negative I h bar times d by dx. Okay. So that means we can say the commutator of momentum and position, like that. That is the commutator of I minus IH bar d by dx with the x operator. Now, in this commutator, right, when you have a constant like negative IH bar, that can factor out. So it's negative IH bar d by dx comma x. Okay. So it is just negative IH bar. Now look, I just did that in my head right after telling you not to do things in your head, right? So how could you check that, right? You could check it by letting it act on a test function. You could say Px is negative IH bar d by dx acting on x, acting on f of x, like that. Okay, so that is negative IH bar d by dx of x f of x minus x times negative I h bar d f dx, like that, okay? And then if you use the product rule, the I h bars are just constants on everything. So it is in fact true that this is negative I h bar times f of x. This negative I h bar, you know, I could write it as negative I h bar hat, like that. But as I said, when these things are just numbers, you're just multiplying by a constant number, like I or h bar, then normally people leave off the hat and just write it as that negative I h bar by itself. Okay, so this is a commutator of momentum with position. Okay, what if we write it the other way? Okay, what if we say the commutator of position with momentum? Well, the commutator going one way, this is xp minus px, right? The commutator going the other way is px minus xp, right? So these things are just negatives of each other. So this is the negative of the commutator of p with x, like that. Okay, so this tells us then that the commutator of position and momentum is IH bar. Okay, so this is an important application of what we've done so far to quantum mechanics, right? So to the typical operators, the position and momentum operators that we work with in quantum mechanics, okay? And so based on this, you know, people would say out loud that position and momentum do not commute. And so, you know, how different is the product XP from PX? Well, this different. IH bar different. Okay, so how are you guys doing with all this, right? I mean, I know I'm dumping a bunch of mathematical concepts on you. Do they make sense, right? These mathematical concepts, okay. So the next homework will include some opportunity to practice with these things, okay? But now we finally want to do something related to the harmonic oscillator. Okay, so let me just set up the two operators that we want to work with for the harmonic oscillator. Okay, so for the harmonic oscillator, I'm going to define two operators. Okay. And so these two operators are a, so lowercase a plus, okay, which is 1 over the square root of 2h bar m omega negative I is the momentum operator plus m omega times the x operator. And a minus is almost the same thing, except that this sign is plus I p hat plus m omega x hat, like that. Okay, so in this notation, omega is the omega that comes from the spring constant, right? We're dealing with a harmonic oscillator that has a particular omega that goes along with the K spring constant. Okay, so here we have these two nice operators, okay? And a short notation is to write these two things together. To say we have A plus or minus is defined as 1 over the square root of 2h bar m omega minus or plus I p hat plus m omega x hat. Okay, so have you seen this kind of short notation before, right? Where I use the plus or minus sign over here, and it goes with the minus and plus sign over there. Okay, so this is like a way of writing two equations in one, okay, where the top sign here goes with the top sign there, and the bottom sign there goes with the bottom sign there, okay? So this one equation really means these two things together. Okay, so these are two operators, right? And they can operate on any function. Okay? So for example, if I have a plus operating on f of x, that means 1 over the square root of 2h bar m omega, then minus I p hat, acting on f of x, plus m omega x hat, acting on f of x. And that means this square root, and then here I have negative I times p hat, which means negative I h bar derivative with respect to x. So f prime of x plus m omega x f of x. And then, well, I can multiply out the negative I that appears 2 times there. And so this is 1 over square root of 2h bar m omega. And this is negative h bar f prime of x plus m omega x f of x. Okay, so this is a made-up operator, right? That does stuff to a function, okay? And it produces another function, okay? Hopefully at this point, you can see what this operator does, but you may still be wondering, why do I care about this operator, okay? And for that, you will have to wait until tomorrow, Okay, so I'm going to stop now and leave you in suspense. And then we'll resume tomorrow and see what we can do with these operators and whether these things will in fact lead to a solution of Schrodinger's equation for the harmonic oscillator. Okay, I'll stop here. I'll stick around to answer questions if you like, or see you tomorrow.